Germany made one of Europe's biggest industrial bets on green hydrogen. Use renewable electricity to produce hydrogen. Use that hydrogen to decarbonize heavy industry, and position German manufacturing at the center of the emerging clean energy economy. Billions of euros were committed to this vision, but the economics have proved far more difficult than expected. Electricity remains expensive. Green hydrogen supply is limited, infrastructure is incomplete, and industrial customers are increasingly questioning whether hydrogen can compete at the scale originally envisioned. So the real question is not whether green hydrogen works technically. It does. The question is whether it works economically, and under what conditions. That is what we are investigating. Germany's hydrogen strategy was closely tied to the future of heavy industry. Steelmaking was one of the biggest targets. Traditional steel production relies heavily on coal, particularly coke, both as an energy source and as a reducing agent for removing oxygen from iron ore. If hydrogen could replace that fossil input, Germany could potentially produce steel with dramatically lower carbon emissions. That made green hydrogen attractive not simply as another renewable fuel, but as a possible pathway for protecting industrial production while meeting climate targets. The vision combined heavy industry, clean electricity, hydrogen production, and national industrial policy into one enormous transformation. At the center of this transition were multi-billion-euro industrial projects. The basic engineering concept was powerful. Instead of using coke in a conventional blast furnace, steel producers could increasingly use direct reduced iron technology. Hydrogen becomes the reducing agent. Electrolyzers produce that hydrogen using electricity and water. Renewable power supplies the electrolyzers, and electric arc furnaces can then convert the reduced iron into steel. But building this new production chain requires enormous capital investment. The plant must change, the energy system must change, and an entirely new hydrogen supply system must develop alongside it. This is why the investment quickly reached into the billions. The attraction of hydrogen comes from a fundamental industrial problem. Many industrial processes cannot simply install solar panels and become carbon neutral. Some processes need molecules, not just electrons. Steel reduction is one example. Ammonia production is another. Certain chemical processes also depend on hydrogen or hydrocarbon feedstocks. Green hydrogen offers a way to replace fossil-derived molecules with hydrogen produced from renewable electricity. So the promise was deep decarbonization. Instead of simply making electricity cleaner, hydrogen could potentially reach parts of the industrial economy that direct electrification struggles to reach. That promise remains one of hydrogen's strongest arguments today. Germany's ambition went beyond emissions. The objective was also industrial competitiveness. If Europe could build green steel early, manufacturers might gain experience, establish supply chains, and potentially export low-carbon products into markets where carbon intensity becomes increasingly important. Industrial zones could connect hydrogen production with steel mills and chemical plants. Ports could eventually support imported hydrogen or hydrogen-derived fuels. Renewable power could feed electrolyzers, and policy could help create an early market for low-carbon industrial products. It was not merely an energy transition. It was meant to become an industrial strategy. And steel was only one part of the story. Hydrogen has legitimate industrial uses. Ammonia manufacturers already consume large quantities of hydrogen. Chemical plants use hydrogen as a feedstock. Refineries use it in several processing stages. Shipping may eventually use hydrogen-derived fuels such as ammonia or methanol. The important point is that hydrogen is not an entirely new industrial product. The world already produces and consumes enormous quantities of hydrogen. The challenge is changing how that hydrogen is produced, from fossil fuels toward low-carbon production, and determining where entirely new hydrogen demand makes economic sense. This is where the economics become difficult. Green hydrogen is fundamentally an electricity-intensive product. An electrolyzer splits water into hydrogen and oxygen. But doing that requires substantial electrical energy. That means the cost of electricity becomes one of the dominant variables in hydrogen production economics. Even a relatively efficient electrolyzer cannot overcome consistently expensive electricity. Capital cost matters, financing matters, utilization matters. But if electricity is expensive, the resulting hydrogen will usually be expensive as well. And that creates a major challenge for countries trying to build hydrogen industries in high-cost power markets. This is one reason Europe's hydrogen ambitions have encountered difficulties. Industrial electricity prices have been under pressure. Developers therefore face a difficult equation. They need large amounts of renewable electricity. They need that electricity at competitive prices. And ideally, they also need high electrolyzer utilization. If renewable generation is intermittent, the electrolyzer may sit idle for long periods. But increasing utilization by purchasing electricity from the grid can expose the project to higher power prices. That trade-off affects the levelized cost of hydrogen. And once the hydrogen becomes too expensive, the industrial customer may struggle to justify using it. There is another problem. Industrial demand for low-carbon hydrogen is potentially enormous, but actual supplies of competitively priced green hydrogen remain much smaller. That produces a familiar chicken and egg problem. Industrial buyers hesitate to redesign plants without reliable hydrogen supply. Hydrogen developers hesitate to build enormous production facilities without guaranteed buyers. And lenders hesitate to finance projects when both the supply agreement and the offtake contract remain uncertain. Everyone may support the concept, but a project becomes financeable only when those relationships become contractual. That gap between potential demand and bankable demand is extremely important. Hydrogen also needs infrastructure. Producing hydrogen is only the first step. It must then be compressed, stored, transported, and delivered to the user. Pipelines may be required. Storage facilities may be needed to balance intermittent production. Ports may support imports or exports. Water supplies must be available. Electric grid connections may need major upgrades. And industrial facilities themselves may require new equipment. So when people compare only the cost of an electrolyzer with the price of fossil hydrogen, they often miss much of the actual system. A functioning hydrogen economy requires an entire value chain. Governments responded with subsidies, grants, regulations, and hydrogen strategies. Those policies can reduce risk. They can support first-of-a-kind projects. They can help finance infrastructure. But policy cannot eliminate engineering and economic fundamentals. A subsidy cannot permanently compensate for extremely expensive electricity. A grant cannot create an industrial customer where no buyer exists. And policy cannot instantly build pipelines, storage facilities, and renewable generation. Permitting, certification, and technical standards also take time, so public support can accelerate hydrogen deployment, but it cannot replace project fundamentals. This is why the current situation should not necessarily be interpreted as the collapse of green hydrogen. A better description is reassessment. The original hydrogen boom was built on several assumptions. Electrolyzer costs would fall quickly. Renewable electricity would become extremely cheap. Hydrogen infrastructure would develop rapidly. Industrial buyers would sign large contracts. And governments would support the cost difference during the transition. Some of those assumptions are developing more slowly than expected. So, developers, companies, and governments are reassessing project size, location, timing, and technology. That is not unusual in emerging industries. This may be the most important lesson. A location can have excellent wind resources, it can have strong solar resources, it can have available land and water, and it can still be a poor hydrogen project. Why? Because resources are only one part of project viability. Bankability requires financing, it requires certification, it requires infrastructure, and most importantly, it requires credible demand. A beautiful renewable energy map does not guarantee an investable hydrogen project. Successful hydrogen development depends on the entire system working together. So this brings us to the second half of the investigation. Instead of asking whether green hydrogen works, we should ask a much more useful question. Where does green hydrogen work? Because the evidence increasingly points towards selective deployment. Hydrogen is unlikely to become the universal energy carrier once imagined. But in the right locations, with the right industrial users, the right power costs, and the right infrastructure, it can still play an important role. The next slides identify those conditions. The strongest opportunities may be industries that already consume hydrogen. Refineries are an obvious example. Ammonia plants are another. Fertilizer production depends heavily on ammonia, which in turn depends on hydrogen. Today, much of that hydrogen is produced from natural gas, so rather than inventing an entirely new hydrogen market, green hydrogen can replace existing gray hydrogen. That has a major advantage. The customer already understands hydrogen. Infrastructure may already exist. Demand is already established. And the engineering challenge becomes substitution rather than market creation. The second condition is inexpensive renewable energy. Hydrogen projects become dramatically more attractive when solar or wind resources are strong and electricity can be produced at low cost. But cheap electricity alone is not enough. The electrolyzer also needs adequate utilization. A project running only a small number of hours per year must recover its capital costs over less hydrogen production. So developers need to optimize renewable generation, electrolyzer sizing, storage, and sometimes grid interaction. The most competitive hydrogen will therefore emerge where both resource quality and system design are strong. Hydrogen also benefits enormously from industrial clustering. Imagine several hydrogen consumers located near one another: a steel plant, an ammonia facility, a refinery, perhaps an export terminal. Instead of every company building an independent hydrogen system, they can potentially share infrastructure. Pipelines become more economic. Storage can serve multiple customers. Ports provide access to imports or exports. And renewable generation can support several industrial loads. This is why hydrogen valleys, industrial hubs, and port-based clusters remain attractive development models. The fourth condition is offtake. A hydrogen project without a buyer is not really a project. It is a production concept. Developers need credible customers willing to purchase hydrogen under contracts long enough to support financing. Banks want predictable revenue. Investors want visibility. Equipment suppliers want confidence that construction will proceed. And industrial customers want predictable hydrogen prices. This means the quality of the offtake agreement can be just as important as the quality of the renewable resource. Strong buyers transform technical potential into bankability. Hydrogen also needs clear rules. If a manufacturer sells low-carbon steel into Europe, customers may need proof that the hydrogen used actually meets emissions requirements. That means hydrogen origin must be tracked. Electricity sourcing matters, life cycle emissions must be calculated, certification systems must be recognized, and trade rules must be understood. Without those frameworks, companies may hesitate to pay a premium for low-carbon hydrogen. Certification therefore becomes more than paperwork. It can determine whether the product actually qualifies for the market it was designed to serve. Perhaps the strongest argument for green hydrogen is that some sectors have limited alternatives. Steel is one, ammonia is another. Certain e-fuels may require hydrogen as a building block. Some high-temperature industrial processes may also eventually use hydrogen where direct electrification is difficult. These applications are often called hard-to-abate sectors. That distinction matters. Hydrogen makes far less sense when a cheaper and more efficient direct electric solution already exists. So the future hydrogen market is likely to focus increasingly on applications where the hydrogen molecule provides something electricity alone cannot easily deliver. Now consider the opposite conditions. Hydrogen struggles when electricity is expensive. Because electricity is one of the largest operating inputs, high power prices quickly translate into high hydrogen prices. Low electrolyzer utilization makes the problem worse. And once hydrogen becomes too expensive, industrial users may continue using fossil alternatives unless regulation or subsidies close the gap. This means location matters enormously. Two identical electrolyzers installed in two different electricity markets can produce hydrogen at dramatically different costs. For hydrogen development, geography is economics. Hydrogen also struggles when projects are isolated. No pipeline means transport becomes difficult. No storage means variable renewable production becomes harder to manage. No industrial buyer means revenue remains speculative. This is why announcements alone are not enough. A developer can announce gigawatts of electrolyzer capacity. But until the project has power, water, infrastructure, permits, financing, and offtake, much of that capacity remains theoretical. The strongest projects solve those dependencies before construction begins. The hydrogen industry may therefore be moving from hype toward disciplined deployment. Instead of enormous projects designed around optimistic future demand, developers may increasingly build projects around specific customers. Projects may be smaller. They may be located directly beside industrial users. They may expand in phases, and they may rely on proven demand rather than speculative exports. That could actually be healthy for the sector. An industry built on fewer but stronger projects may ultimately grow more sustainably than one built on announcements that never reach construction. So what projects are most likely to survive? They will usually combine four things: cheap power, infrastructure, reliable offtake, and supportive policy. Notice that electrolyzer technology is not even the only deciding factor. A world-class electrolyzer cannot rescue a project with expensive electricity and no customer. Likewise, excellent renewable resources cannot compensate for missing infrastructure forever. The winning projects will be those where the entire commercial and engineering system fits together. That is the difference between a hydrogen concept and a bankable hydrogen project. Germany's experience does not prove that green hydrogen has failed. It proves something more useful. Green hydrogen is not automatically viable simply because governments support it or because renewable resources exist. It works when the economics, infrastructure, engineering, and demand align. The future therefore belongs to projects with low-cost power, existing or clearly identified customers, strong infrastructure, and credible commercial structures. Germany's multi-billion-euro experiment may ultimately become one of the most important lessons in the hydrogen transition. Not that hydrogen cannot work, but that hydrogen must be developed selectively, where the entire system makes sense. And that may be the difference between the projects that stay on PowerPoint slides and the projects that actually get built.